I'm going to give you an excerpt from a BLDB tutorial that we'll be presenting in BLDB in August. So consider this as a little sneak preview on self-configuring systems. Now, it pretty much goes without saying that there are massive amounts of data that are being collected in pretty much all fields, from businesses to science to entertainment, with the purpose of analyzing this data and extracting deep insights that will then automate various processes in decision making, such as advertisement placement, personalized recommendation, optimizing business customer relationships, and so on and so on. Now, this need for analytics has led to considerable amount of innovation for systems for big data analytics. Going back 20 years with massively parallel data warehouses to Hadoop MapReduce, Spark, Flink, and of course, the ecosystems that grew around them. Now, for this presentation, I'm going to focus mainly on the Hadoop and the Spark ecosystems for big data analytics. So both of these ecosystems run on distributed share nothing clusters. There's a distributed file system on top, HDFS being perhaps the most popular of them all. Then there are resource managers responsible for managing physical resources of the cluster, CPU, memory, etc. And then on top of that, we have Hadoop and Spark, two perhaps of the most popular systems for analytics today, with the various systems on top of them. Now, the thing is, with all these systems, they're wonderful, they're very popular, but actually, setting up a cluster and configuring the system and executing your analytics workload actually takes a decent amount of effort. And we'll go through that in a little bit. But I want to start with a very, very simple example. Let's say we have some data scientists. They want to execute some analytic workload. They have some performance in mind and so on, and they want to use Spark or MapReduce to set things up. But there are at least 3 different levels of decisions that they need to make before they can get the system up and running, in a performant way. The first level of decision comes at the level of resources. How many machines should I use for this? What kind of machines? How many resources? If we're talking about the cloud, we need to decide, how many instances should I rent? Then come platform-specific configuration settings for the different systems. Both Spark and Hadoop have a lot of different parameters that affect the size of containers and how are those allocated, scheduling decisions, and so on and so forth at the level of the platform. And then finally, you have job-level configuration parameters that affect things such as task parallelism, whether to use compression, what kind of memory settings to use for the different tasks, and so on and so forth. So overall, there are a lot of different decisions that a user needs to make in order to execute an analytics workload. Now, how bad are things? If I just focus on the job level, configuration parameters, there are almost, there are around 200 different parameters for both, Hadoop and Spark that can actually have a significant impact on performance. And this, the performance is also depending on the kind of hardware we're using, and of course the application itself. But actually, it's even worse, because you have a lot of different parameters that can affect performance, but they can also affect performance in different and weird and interdependent ways. Here I have 2-dimensional projections, essentially 2-dimensional surfaces with running times of 2 fairly simple applications, while varying 2 different parameters. It doesn't matter what the parameters are, the controlling memory, but what we see here is that by varying these 2 different parameters, we get different performance. And the optimal setting for one parameter is actually affected by the setting of the other parameter, which makes the problem of figuring out, what kind of settings should I use even more complicated. And a keen eye will also notice that the settings are actually different from these two very simple applications. And different applications require different parameters. So that led to a lot of people to start thinking about this problem. How do we automate all of this? We showed 3 levels of configuration options. How do we automate the process of configuring and running data-intensive workloads in order to meet the various user requirements? And I've already alluded to some of the challenges, but let's go through them one at a time. First, of course, we have a very high-dimensional space. Lots of parameters with different interactions between them. And as we've already seen, there's a nonlinear effect that the hardware, the applications, and the parameters can have on the application performance. Now, what of course makes things even worse is that both of these systems use higher-level programming languages like Java or Python or Scala with a lot of user-defined functions that are very hard to model and figure out, how is the performance influence based on the application. Then, of course, is the input data. The good old database world, you had tables and you had schema information and you had all sorts of statistics. Here you have files with data that you probably won't even see until you actually read them to process them. So you don't have any information about your data as well. And of course, just a little cherry at the top, we're talking about terabyte scale data. We're not talking about a couple of gigabytes. We're talking about lots and lots of data that we need to process as efficiently and effectively as possible. So of course, there's been a lot of research work in this field trying to address these challenges. I've been, me and some collaborators, I've been looking into, put together a survey on this, and we have found over 100 different really good quality papers over the last 10 years that are actually trying to address, some form of this problem. And we look at all of these approaches, we can actually categorize them in 5 different approaches. The first category of approach, which we'll call the cost modeling approach, tries to use cost models, mathematical models, essentially, and statistics to model, okay, this is the applications, the input data, et cetera, and how that affects performance in order to optimize it. The second category is the simulation-based approach, where they built a simulator, and they tried to use the simulator to figure out how exactly the system should behave, and then use that information to tune the system. The third category is the experiment-driven approach. This is the approach that essentially says, okay, let me actually run my application with different settings in some, of course, structural and smart way to figure out what the best settings are to use for executing this application. Fourth category is the machine learning approach. Use machine learning in different ways, and we'll see that it's been very creative in some of the ways they're using machine learning to tune application performance. And then finally, we have the adaptive approach that tries to change configuration dynamically while the application is actually running. Right, so I'm going to go through some of the key papers in each of these regions, offer some highlights, some pros and cons of the different approaches, and see where that leads us. So, as far as cost modeling goes, right, the idea is to essentially use a set of equations to model the performance as a function of the actual program, the input data set, the cluster resources, and the configuration settings for each job. Now, if we can do that in an accurate way, then we can formulate all sorts of interesting optimization problems. Perhaps the simplest one is, given my program and my data and my resources, I want to find the set of configuration settings, the job level configuration settings that will actually optimize the performance of this particular job. So the Starfish line of work that we did several years back was actually the first job that applied cost-based optimization in the world of MapReduce and introduced a CostBased Optimizer. Now, the idea behind it was based on essentially 3 steps, what we call the profile, predict, optimize approach. So in the profile approach, the idea is to actually collect some information, some summaries essentially of execution that you can later use for your models. The second step, the predict step, is to actually use all these different mathematical models to estimate what the impact of different changes will be, right? What happens if I change some configurations? What happens if I change my input data size? What happens if I were to increase my cluster size? You know, how all of these affect performance. And then finally, the optimize step, where you enumerate this large space of different configuration choices, and then trying to pick the one that gives you the best performance. So going through them briefly, right? So when it comes to profiling a MapReduce job execution, the idea is to actually execute the MapReduce job, or a small sample of that MapReduce job, in order to collect some information, which we call an execution profile. So what this profile is essentially a summary of execution consisting of various statistics and counters. Now, a couple of little details. We actually use dynamic instrumentation in order to collect all of this information from unmodified MapReduce programs, so the application developer didn't have to worry about them, and also use some specialized sampling techniques to minimize the overhead of this type of profile. Now, once we have this execution profile, then we can build the different models. And different models are required to model different aspects of the system. So we used a combination of models ranging from some classical cardinality models inspired from the database fields to relative black box model, analytical models, and so on. And the idea was that given a profile, an execution profile, then based on a particular set of input data, or cluster resources, and configuration, and of course using the models, we can build a predicted or a hypothetical execution profile for a job while being executed on these type of settings, right? So this hypothetical execution profile will give you a very good idea of how this particular job would perform. And once you can get an accurate execution profile, then you can turn it into and optimize it. So for the optimization step, we're interested in finding the optimal configuration setting. So we have the execution profile. When I run the job on some new input data or perhaps a new cluster resources, the job optimizer is responsible for enumerating the different options. Again, there's some smartness that needs to go in there because it's a very large space. And then we use a technique called recursive random search to search through this space to find the best configuration settings we can use. Then we took this a step further and said, let's tackle the resource provisioning problem, where we wanted to execute this job, but we were free to select our own cluster, perhaps from a cloud provider or from a set of machines we already had, in order to, in addition to the best configuration setting, also find the best resources, right? Essentially the best physical resources, in order to minimize performance while taking cost into account, if this was a cloud setting, or minimize cost while taking performance into account. Now, afterwards, there was a bunch of other jobs that essentially address the same problem, trying to optimize at configuration parameters at different levels using different approaches. These are a small sample of perhaps the most impactful work. The main difference comes in the type of optimization. People, we've used recursive random search, others use Lagrange multiplier or grid hill climbing or genetic algorithms and so on and so forth in order to get the job done. Now, as far as Spark goes, there's a lot of work here as well, Interestingly though, most of them actually focus on one particular scenario, the scenario of profiling using some small clusters and small data sets, and then trying to predict and optimize the performance on large production clusters with much larger data sets. And once again, there are different types of work. They have, some of them focus on machine learning applications. Other ones are using white box models with simulation. I'll get into this a little more, and so on and so forth. So at the end of the day, the cost modeling approach gives you a very efficient way of predicting performance, because all you have to do is essentially plug in numbers into a set of mathematical equations, right? And then you get the answer out of that. And it gives you fairly good accuracy in a lot of scenarios. The problem though is that we're talking about distributed, very complex systems, right? So it's very hard to model every little detail using just mathematical models, right? So a lot of the times these models are based on some simplified assumptions, either for with regards to the data properties themselves, or with regards to the application characteristics and so on. It's also very hard to capture some of the system internals and some of the pluggable components. For example, if you start, you change the scheduler, all of a sudden, most of your, half of your models might not work anymore. So to address essentially this, complexity of the systems, there's a lot of people who came out and said, let's just build a very good simulator that will simulate how MapReduce actually executes, and then we can use that to predict and optimize. And I'm saying MapReduce here because to this point there is no Spark simulator available for doing the same thing. So a simulator can be used, of course, for finding the optimal configuration settings, but it can also be used for other interesting use cases, such as identifying performance bottleneck or testing new pluggable components such as schedulers. And all the simulators that I've seen are essentially using discrete event simulation to build the simulators. So we're only going to see one of them, HSIM, which is I think the latest Hadoop simulator. The idea is, you give some input to the simulator, and this input typically comes to the form of essentially two text files with some information. One file has information about the job itself, some configuration parameters and properties of the data, and also some cluster specifications. These are my nodes, this is the topology of the network, and so on and so forth. Then the simulator will essentially take this node, build a virtual cluster, right? I'm talking about in memory in a single process that will consist of the main components of the MapReduce platform. So there's going to be virtual job tracker, virtual task tracker, there's going to be heart beating going on, and then the job is going to get simulated. The tasks are going to get generated, sent to the task trackers, and so on and so forth. And the output of the simulator is going to be a very detailed, very fine-grained execution trace that really details how this job would be executed on a real MapReduce cluster. And this, again, like before, there's a bunch of different Hadoop simulators out there, and we'll see, some of them will simulate network traffic, some of them will not, some will simulate hardware properties, like what type of CPU do I have, how much memory do I have, some of them will not, and then so on and so forth. So, there's pros and cons with all of them. Of course, I won't go into any of the details right now, but at the end of the day, the simulators are very good at providing very high accurate estimates of how exactly the job is going to perform, right? So compared to the cost model approach, these are typically far more accurate. And they're fairly efficient for predicting, the performance of a job. It might take, depending on the simulator, a few seconds, maybe a minute to simulate, a multiple hour job. That's great if you just want to do that. Now, if you want to optimize and find the optimal settings, which typically involves, oh, let me simulate this job with 1,000 different settings, that can be very expensive and fairly slow, and much, much slower compared to the cost-based approach. There's some other disadvantages. It's very hard to capture some of the more dynamic cluster utilization patterns. And again, there are some components, some interactions, especially when we start talking about multi-tenant clusters, that even a simulator approach will have hard time modeling. The third category is the experiment-driven approach, right? So the idea is, these systems are very complicated. It's hard to model. It's hard to simulate. Let's just use them. Right? Essentially, that's the key idea here, right? So the high-level idea is, okay, I have my MapReduce or my Spark application, I have some input data or perhaps a sample, right? What do I do, right? Okay, I submit it, and there's typically this thing called a parameter search engine. This is the entity responsible for deciding what kind of configurations to use. So it will select some configuration settings, it will send it for execution to my Hadoop or Spark cluster, and then there's a performance analyzer that's going to look at the logs, figure out, okay, how did this configuration work? Did my job perform well? Were there any bottlenecks? And then based on this feedback, this parameter search engine will generate a new configuration setting, and then the process repeats, right? And will repeat several times until a good parameter settings comes out of it. So as you can imagine, all the smartness goes into this parameter search engine, right? And there are different approaches. For Hadoop, there are two different lines of work. One that uses some sort of a grid search, trying to figure out how to generate essentially different points in this large configuration space and execute them. And there was this other approach that used a genetic search algorithm, essentially with some feedback approach to figure out, okay, I've seen this configuration setting, I've seen this, let me explore this area and that area, until it converges to some good parameter settings. For Spark, there are some other approaches. There's a search tree approach, and then more recently, last year, there's a multiple bounded search algorithm that was again proposed within this framework to generate some good parameter settings. Of course, I won't go into any of the details. The idea is to get the high-level view of this area. Yes?
Can you give us a sense of how much time it takes for this exploration to take place?
Mm-hmm. So most of this, let me think which one I remember the most. Okay, so down here in these two MapReduce ones, it runs in the magnitude of, I would say maybe a few hours for running, a workload to get, a good set of parameter settings. Right. So, as you can imagine, this approach makes a lot of sense when you have a particular workload that you're going to be executing for many times. You have some report generation workload that you're going to be executing every day for the next 2 months. Yeah, it's worth spending a few hours to optimize this particular type of workload. Of course, if you have an ad hoc query or that you want to execute here, this is definitely not the best approach to use.
What are these parameters? I mean, okay, it's like HDFS replication.
There's all
like
sorts of parameters
you cannot count, right? I mean, the replication of the HDFS layer is going to give you more fault tolerance, but it's not going to change the result at all, right?
Right. Well, so for MapReduce, you have number of reducers, you have different, whether to use compression or not, you have all sorts of different memory settings, how big the buffers will be, whether to use a combiner or not. There's settings that affect the shuffling, and so on. And for Spark, there are similar settings. There's a lot of memory settings for Spark, compression, like MapReduce, and a few other settings. Yeah, there are about 15 to 20 parameters in Spark that will affect the performance of the applications at a significant level.
So do you have indicative executions of, let's say, worst parameter, test parameter, just to give me an insight into how much I would think by tweaking this?
It really depends on the application and the cluster. We've seen anything from, I think best case scenario could go up to even like an order of magnitude difference compared to, and those are probably the extreme, but 2 to 5x, yeah, it's reasonable. A lot of approaches will give you, 2 to 3x. Yeah.
But about the data, maybe for different data inputs, you have different configurations.
Yeah, of course. So the input data is always part of this because the input properties have a significant effect. And this is one of the limitations of a lot of the approaches. Because you don't have insight into the data. You don't know in advance what the data is going to look like. That's why a lot of applications or a lot of approaches require that you actually sample with the actual data that you intend.
Go for it.
Yeah, so thanks. Just wondering, are these parameters all correlated? I mean, what happens if I, like for example, optimize them independently? Would that be easier?
That would be much easier, but almost everyone is agreeing that that's not a good thing to do because there's a lot of correlation between them. And that was, I guess, the point of the two graphs that I showed earlier. You might optimize the first parameter and says, oh, 100 is a really good choice. But then you go and optimize the other parameter, and because of this 100 here, for this parameter you get 20, whereas the optimal would have been, I don't know, 60, 40 or something, right? So there's a lot of interdependencies between the parameters.
So a lot of results showing that?
Yeah, there's a lot of results showing that. Not pairwise and triplet-wise, yeah. There's been a lot of analysis. There are papers designed just to show how complicated this, that they've done lots of experiments to show how complicated this problem really is. Yeah.
So,
Yes.
So just to make things a little more intractable, right? So, so we look at the application and it seems to be like a black box that, some piece of code you can run and so on. Right?
Yeah.
And we're trying to guess what this application is doing and how it's interacting with the runtime system and so on. So is there some way to describe the application more than just as a black box piece of code? I mean, so I'm trying to look for, is there some insights in how to, abstract what the application is doing?
Yeah, so most of the approaches that I'm describing here do treat the application as a black box, but there are other approaches that are trying to do some static code analysis, for example, to figure out, oh, this application is actually doing some sort of a filtering inside, or it's doing some sort of a weird analysis that will blow up the data from one stage to the next. So there are a couple of approaches that are trying to do that, but because most of these applications are high-level code, you could do anything you can imagine, right? You can write Java code, so you can do pretty much anything. It's very hard to do. Now, in the interest of time, I'm going to move on a little forward. Okay, so we set this because I really want to go through the machine learning approaches as well. So the machine learning approaches, there's typically an offline training phase and an online prediction phase. The interesting aspect is there are actually 3 different ways to use machine learning. At least there are 3 different ways that people have used machine learning in this setting. The first idea is to build a historical store, right? So the idea is you take a set of MapReduce jobs, you execute them, you collect some data about them, right? And then you store a set of features along with the execution time, where the features could be the name of the job, how many tasks it used, how big was the input data, etc. So then when a new MapReduce job comes in, you can do something like k-nearest neighbors to find some of the similar jobs, probe the store, get the execution times, and in order to predict the execution time. So that would be one way to do it. Another way to do it would be, again, execute the job, collect information, but this time store the job profile instead of just the execution time. So now when a new MapReduce job comes in, you do a little sample execution, extract the features, probe the store, get the job profile, and then use that to optimize the performance. A different way of using machine learning is actually with clustering. So the idea is you execute jobs, you collect utilization data, CPU, memory, etc., and then you cluster the job based on the utilization data patterns. And then you can build models for each cluster, so when a new MapReduce job comes in, you do a little sample execution, you see the utilization pattern, you see which cluster it belongs to, and then you take that, the model that you've built. And this is a similar approach, I'll skip it. All right, and then the third way of using machine learning is by directly modeling the app itself. So the idea here is you take the MapReduce job, you execute it using different configuration settings to build your training data, and then you generate a machine learning model. So now when that same job comes in, then you can employ the machine learning model to get some execution time prediction and then use a search algorithm to find the optimal configuration. And of course, there are different approaches using regression or decision trees for the modeling. You can use genetic algorithms or recursive random search for the search algorithm, etc. The thing with this approach is that the offline training phase is actually fairly expensive. If I remember correctly, RF Hog was saying that it needs around 2,000 executions to build a really good model, right? That's a very high number of executions just to build a model for that one particular job. And this is per job, so every job has its own model. So yes, you can get really good performance using machine learning. You can capture all sorts of different crazy system dynamics, but it's very expensive in terms of training data set, of collecting the training data sets. And then finally, I guess we're running out of time, the adaptive approach. I won't go through it, I'll just show the animation. The idea is you use some configurations for some of the tasks, collect information, based on that, you find other configuration settings, and you move on, there are different approaches. But at the end of the day, if we were to put everything together, we can generate this giant table here that gives you a lot of pros and cons for all the different approaches, which at the end of the day tells you that to this day, not a single approach is able to give you very good prediction accuracy and low overhead in most scenarios. So you just spent the last 30 minutes of your time telling you that we cannot solve this problem. Sorry about that. But the good news is that this is still a very hot open research problem. It's a very challenging problem. And it's definitely a lot of people still looking into it. All right, thank you.
So thank you. Do you have any questions from the audience?
So have you seen any approach attempts to marry different approaches, like the active with the machine learning? So let's split the cost.
Right. That would be. I've seen some approach. A couple trying to mix cost modeling with simulation or cost modeling with machine learning. In some aspects of it, but nothing very concrete that can get the pros of both approaches without the cons. Not yet. But a hybrid approach would definitely be a very promising step.
So my last question is that do we know about accuracy? Any with respect to which one of these methods is more accurate? So I might want to invest in that. Is it experimental or the machine learning, or we don't have such a knowledge?
Well, let me think. No, I don't think anyone has actually investigated those. Based on the results that they, the individual authors claim, the experiment-driven is typically very accurate because you actually run it and see it. But then, so people who do simulation also claim that they get very good accuracy.
So, thank you.
Thank you.
We are again 10 minutes late.